All right. Well, guys, another recorded lesson, but the next one we're going to do together live and in person. But here we are. Today's lesson, Unit 1, Lesson 3, is all about the periodic table. So I just want to take you back. So far, we've learned about the basic structure of the atom, but today we're going to talk about the periodic table of the elements and how we use it in modern chemistry. So I want to go through a bit of history. And early on, they attempted to organize the elements in the early 19th century. And there's a gentleman named Johann Wolfgang Döbereiner, and this is a German chemist. He's one of the first to notice that there's some trends in the physical properties of the elements. So there's some trends in the way elements behave. So this is Döbereiner. And Döbereiner noticed that certain elements could be placed in groups of 3 similar elements that had similar traits. So he found that when he did this, so he'd take groups and he'd say, okay, these all react with water, so I'm going to make them one group. And then he would take another group and say, well, these are all stable and gaseous at room temperature, make them a group. And he would divide all of these atoms into groups of 3. And he found something, which was that when he did this, he could find the atomic weight of the atoms. They had a way to do that already. And he would find that the weight of the central atom of the 3 was roughly equal to the average mass of all 3. So he called these groups triads. I'm going to show you here. So these are the groups he came up with. His first triad was lithium, sodium, and potassium. And if you look at the 3 of them, lithium has a mass of 7, sodium has a mass of 23, and potassium has a mass of 39. And if you take the average, you'll see that you get 23, which is about the mass of sodium. And you looked at this group, calcium, strontium, and barium. They all behave the same. Calcium, strontium, and barium all have really similar physical properties. And again, if you line them all up and take their average mass, it works out to 88. And strontium has a mass of basically 88. Likewise, chlorine, bromine, and iodine are all reactive gases at room temperature. And again, he added their 3 masses together, and the average mass worked out to be bromines. And this goes on with sulfur, selenium, and tellurium, again, 79 and 80, carbon, nitrogen, and oxygen, and excuse me, iron, cobalt, and nickel, which he calls iron ferrum. And again, the average mass works out to be the mass of cobalt. Now, Döbereiner's triads is actually a good start. His triads line up with some of the groupings of the modern periodic table, but they're obviously not perfect. They're not complete. So despite the usefulness of this system, one of the things to keep in mind is that these atoms are all that's in it. And so 80% of the elements, even of Döbereiner's day, didn't fit into one of these groups. Right, so again, this is just another way of showing it. These are Döbereiner's triads. You can see lithium, sodium, potassium are together. You can see calcium, strontium, and barium. Phosphorus, aspartame. What is SB? I'm having a moment. I can't remember. Anyway, sulfur, selenium, and tellurium, chlorine, bromine, and iodine. So you can see that he has his groups here, and you can see that his groups, antimony, by the way, it's antimony. Anyway, you can see that his groups line up with how these things are grouped on the modern periodic table. So he is onto something, and he's found something meaningful. But he didn't take it anywhere after that. But this is the first person to really start thinking about how different elements group together and how their properties might have some central trends. This brings us to a fellow named John Newlands. And in 1864, he proposed his own organization. So like on the modern table, Newland organized the elements according to their atomic mass. His was the first to assign hydrogen a mass of 1, for example. But he noticed that every group of 7 atoms displayed similar characteristics to the next group of 7. And he called these groupings octaves, just like in musical theory. So if you look, Döbereiner, he groups them into groups of 3 and finds common trends within the 3. Newlands puts them in groups of 7 and says it's not that those 7 atoms have the same trends, rather it's that those 7 atoms all have different trends. But then if you go to the next group of 7, they have trends really similar to the first group. And so he thinks of this as being like in music with an octave. So for example, actually I have a guitar right here, so why not? In music, you have a scale that would go like this. And then starting on that next note, we can do the scale again. And it's the same pattern, it's just a little bit higher. And so Newland says that these elements actually behave in the same way, where if you start looking at periodic tables, you'll hear trends. Oh. And so this idea is that maybe not only can these things be grouped, like Döbereiner did, by things that are similar, but also we can group them in a way where there's a repeating pattern. And again, he actually writes them out as if they're on a musical staff, where he says if you go hydrogen, lithium, beryllium, boron, carbon, nitrogen, oxygen, oxygen, you get a set of behaviors, and then the next group lines up. So fluorine behaves a lot like hydrogen, and sodium behaves a lot like lithium, and magnesium behaves a lot like beryllium, and aluminum a lot like boron, and silicon a lot like carbon, and phosphorus a lot like nitrogen, and sulfur a lot like oxygen, and chlorine behaves just like fluorine, which behave just like hydrogen. And so he says that this trend continues. Potassium behaves like lithium, calcium like beryllium, and so on and so forth, all the way up. So just like a musical octave is the same pattern repeating, right? That is Newland's idea. The problem is if you look, all of a sudden, the behaviors get weird. It goes right up to fluorine, where this pattern works really well. And it does, by the way. He's not missing anything. Up to fluorine, this octaves rule actually works really, really well. But then all of a sudden, you get magnesium, aluminum, silicon, and you get, after manganese, you get iron, and then cobalt, and then nickel, and then things just start completely misbehaving around here. And it no longer fits the pattern. Now, Newland's table became disorganized as you moved along it. It was perfect up till calcium, and then it gets worse and worse. And it started to make some mistakes. It started to place metals in the same group as nonmetals, and other errors that were obvious, even to scientists at the time. And so as a result, his work was largely discredited. In fact, his paper was never even published at the time, and he returned shamed to working as a chief chemist at a sugar factory. But we know that this is because he failed to account for elements that hadn't yet been discovered. So he was on exactly the right track. His problem was that they had not yet discovered all of the elements. And in fact, despite the fact that he met with shame, had he stuck around until they had discovered a few more, his theory actually would have been just right. But this brings us to a guy named Dimitri Mendeleev. And in 1869, Dimitri Mendeleev published his periodic table. And just like Newland's, Mendeleev's table placed the elements in order of their atomic mass. All right, so going from lightest to heaviest. Mendeleev realized that groups of elements that shared specific properties should be placed in groups. And that, by the way, if you remember, is the same idea that Döbereiner had, right? He said that things with similar properties should be put together in a group. So lithium, sodium, and potassium should be in a group. Calcium, strontium, and barium should be in a group. And Mendeleev sees the same thing. And so exactly like Döbereiner's triads, Mendeleev takes these and he puts them into vertical columns. That's Mendeleev, by the way. And putting these elements into columns by their physical and chemical properties, he also put them into rows based on the same repeating idea that Newlands had. But when he did this, he found that there were blank spaces, where he said, oh, if I put all of these in columns based on their properties and in rows based on their mass, I end up with blank spaces. But rather than view this as a problem, Mendeleev, and I love the arrogance of this. To me, there's such a brilliant mind that says, there's a gap in this table, and I don't think it's that I'm wrong. I think it's that we just haven't found an element yet. And that's what he assumes. He assumes that those spaces must just be elements that haven't been discovered yet. So he put them on the table anyway. And he made predictions about them. He said, in this space must fit an element that we haven't found yet. And when we find it, it's going to be a metal, and it'll weigh around this range, and it'll be reactive like this. And he made all these predictions. And as time moved on, even in his own lifetime, these elements were actually discovered, and their properties matched, more or less, Mendeleev's predictions. Right? This, by the way, is Mendeleev's periodic table. And you can see it's not quite exactly the same as ours. And you can also see it's full of some question marks and some gaps. It's based on incomplete information. And if we look and sort of put Mendeleev's periodic table into sort of slightly more modern look, we see it would look like this. So it's by no means exactly the same as our periodic table, but it follows a lot of the same trends. You can see that the rows basically match our own. And everywhere where you see something pink, we have something that was not yet known to Mendeleev, and yet he left space for them, which is pretty amazing. So that's the end of this lesson. It's a fairly brief one, which is good because we took some time early in the period to take up homework. And there's no homework associated with today, so you guys get a weekend off, which is nice. But when we get back together on Monday, I'll deliver the lesson in person, and we'll carry on from here. We're still going to be talking about the periodic table on Monday, but we're not going to be talking about like this sort of historically. We're going to talk about it in a very modern sense and how we use the periodic table today and what it can tell us. And we have a wonderful weekend. Come check in with me because I want to talk to all of you about your papers and where we're off with that. So have a great day after talking to me.